Okay, so now in this part, we will learn how to work with elastic strings. Okay, so in the previous video, we discussed about how to work with elastic springs. So now it's all about elastic strings. Okay, so the mechanism will be slightly different. Okay, let's see. A particle P of mass 0.8 kilogram is attached to one end of a light elastic string of natural length 1.6 meter. And the modulus of elasticity 20 newtons. Let's write it down. Natural length is 1.6 meter. Lambda is 20 newtons. The other end of the string is fixed to a point O on a smooth horizontal surface on which P rests. The particle is held at rest with OP 2.6 meters and then released. Guys, can you see how the diagram looks? So you have like this. So you have the other end of the string is fixed to this point O. So from point O, you are going to draw the string. The natural length of the string is 1.6 meters, right? Natural length is 1.6 meters. Natural length is 1.6 meters. And then the other end of the string is fixed to point O, okay, on the smooth horizontal surface on which P rests. The particle is held at rest with OP 2.6. Guys, what have we done here? If OP is 2.6 meters, what have we done to this elastic string? It has, we have pulled it, right? We have an extension here because we have pulled the string to a distance of how much? How much are we initially pulling it? So initially we are pulling it to a distance of Initially, we are pulling it to a distance of OP is 2.6, natural length is 1.6. O to P is 2.6 means we have pulled a distance of how much? 1 meter. And I told you the amount that you initially displaced from the natural length becomes immediately what? The amplitude. So amplitude is 1 meter. The amplitude is 1 meter. Amplitude is the maximum X value. That is 1 meter. Okay, and then okay, so the question says show that while the string is taut. So while the string is taut, P moves is simple harmonic motion. Okay, so you need to understand that there is something going on here. They say while the string is taut, right? So where is the string taut? String is taut. A string is taut when it is always what? Stretched beyond its natural length. Isn't it? Because now the difference in this question is you are now dealing with a elastic string. Okay, previously we dealt with elastic springs. In a spring, we had extension and we had compression. Extension and a compression. But in a string, you can see while the string is stretched beyond the natural length, you will have the string will be taut, which means taut means there is tension in the string. We have tension in the string, but when the string becomes slack, you realize that there will be no tension, right? Are you with me? So when the string becomes slack, there is no tension. Okay. So while the string is taut, you have to show that P moves with simple harmonic motion. So shall we show that? How do you do this? You have to consider the particle at a general point. And where is the center of the SHM? Always center of the SHM will be in this case where the object would want to stay naturally, where the string would want to be natural. Where is it naturally wanting to stay? So naturally it would want to be over here, right? At the natural length. So this is the center of the SHM. Okay, let's draw the another diagram. So this is point O. Okay, and then you have to consider the center. This is the center. And then X is the distance measured from the center. X is the distance measured from the center. Can you see? Natural length is 1.6 meters. Okay, so I have considered a general point now. Can you see? It's lower than the amplitude. Okay, so this is a general place where the object is moving. It's lower than the amplitude. Are you with me? So how do you show the particle moves in SHM? How do you prove the particle moves in SHM? You have to prove the characteristic simple harmonic motion equation, which is what? X double dot equals to minus omega square x. Okay, so let's apply that equation. So to apply that, we are going to use F equal ma. What are the forces acting on this particle at this general point? You have the tension, right? You have the tension. What else? You have tension. What else? That's all, right? Weight, normal reaction are acting vertically. So they will not make an impact. Okay, for the horizontal motion, only the tension. There's no friction. Therefore, we only have the tension. So we will apply now what? We will apply F equal ma away from the center. That's how we do it. Always apply F equal ma away. So tension will be minus T equals mass is 0.8 into acceleration is x double dot. Are you with me? Calculate the tension. Tension is lambda x over L. So what's the lambda value? Lambda value is 20. Extension is the length the string has stretched beyond its natural length. Extension is x, right? Over natural length is 1.6. Are you with me? So I think you can see the initial part of the sum does not change, right? So this was the same as what we did in the previous part with the elastic spring. Can I know how much is 20 over 1.6? 20 over 1.6, 12.5x. So let's input the value here, minus 12.5x equals 0.8 x double dot. So x double dot equals minus 12.5 minus 12.5x over 0.8. Are you with me? Can I know the simplification of 12.5 divided by 0.8? That is 125 over 8, right? 125 over 8x equals to x double dot. Or you can make it decimal 15 point. Now the minus is there. Minus 15.625x equals x double dot. If you are going with the decimal, do not reduce any decimal. We need the full exact, or else I would suggest you to go with the 125 over 8. Okay. So can you see we have the characteristic equation of SHM? X double dot equal minus omega square. Therefore, you can write particle P moves with SHM. Okay, so therefore P moves with SHM. Okay, so we'll move on to part B now. Calculate the time from the instant of release until P returns to its starting point for the first time. So you can see this is the point where we release P. We release P at the amplitude, right? So whatever the distance you pull from the natural length, I told you that becomes the amplitude, the initial amount you pull at the beginning. So then you release it from here. So this is the time 0. Can you see? This is the place where you release. And then they are asking you to calculate the time from the instant that you release this particle until it comes back to its starting point. Okay, so now this is where the difference occurs between springs and strings. Okay, so now, when it comes to this SHM, simple harmonic motion always occurs only and only when the string is taut, because if the string is taut, you have tension and you need to have tension in order for this particle to perform simple harmonic motion. Okay, so what's the problem that we face here? I think you can see from the amplitude and until you come to the center, there's no problem. Okay, the string is taut, the string is beyond the natural length, so that's perfectly fine. But look, what happens when you reach the natural length? What happens when you reach the natural length? The moment you reach the natural length, since this is a string, right? It's not a spring, it's a string. So when it comes to a string, the moment you reach the natural length, the string becomes slack, which means what? You lose the tension. So the moment you reach here, Okay, so let me draw another diagram. Okay, so let me show this. So the moment you reach this point, this is point O. So from here, the moment you reach this point, can you see? What is the point? This point, this is the point where you reach the center. Are you with me? The moment you reach the center, actually what happens to this string? The string, immediately now you can see that you started the motion from the amplitude. Are you with me? So this is the amplitude, and then this is the center of your section. Are you with me? This is the center. So amplitude to center, the string was taut. There was no problem in that. Okay. But now once you reach the center, what happens to the string? The string becomes slack, right? So when the string becomes slack, can you expect the simple harmonic motion to continue? No, right? So by the way, at the point you reach the center, you have the maximum velocity also. Are you with me? You have the V max, isn't it? You know, when you reach the center of your SHM, you reach V max. So with the V max, and now suddenly the string is actually what? Becoming slack. So now can you predict how this particle will move? Is it going to stop here? Obviously, no, right? It has a velocity. So how do you predict this particle will move? The next part of the motion. Is it going to continue simple harmonic motion? The first question, is it going to continue simple harmonic motion? No, simple harmonic motion cannot occur when the string is slack. So if the string is slack, and you know there are no other forces here, right? If the string is slack, it means there's no tension. There's no friction. So is there any external force acting on this particular object? No, which means what? Which means what? This particle, will it, how will it start to move now? Will it start to move with acceleration, or will it start to move with deceleration, or will it start to go with constant velocity? You know, acceleration occurs if the velocity will differ. It will increase or decrease depending if there is an external force. So are there any forces applying on this object now when the string becomes slack? No, right? The only force acting on this was the tension. And once you reach the natural length, the tension is gone. And you have a speed, and you have achieved the maximum velocity to this side. So what's happening? From this point onwards, the particle will start to move what? As a particle moving with constant velocity. So it will start to move with constant velocity because there are no external forces. So how far will it continue this constant velocity? How far will it continue with constant velocity? It will move over here with the constant velocity. Will it stop at O? Is there a reason that it needs to stop anywhere? It will continue to move, right? It will continue to move past O. It will continue to move past O to the other side because you have fixed the string to the point O on the floor, isn't it? So then you are going to continue to move to the other side. How far are you going to continue? How far will this object continue with this motion? Until it goes another natural length of 1.6 to the other side. Until it moves a natural length of 1.6 to the other side. So from this point, let me show it to this point. Okay, so this was the natural length 1.6 meter, right? So it will move another natural length 1.6 meter to the other side with this maximum velocity. So over here, the particle moves with constant Vmax velocity. Constant. The particle is moving with the constant Vmax velocity. Because over here in between, the string is completely slack. The string is completely slack. So over here, when the particle is moving, the string does not play any part in here at all. The string is completely slack. And now what's happening on the other side? And after you reach the other side, what's going to happen? Suddenly, now the particle comes over here, right? And then suddenly now the string feels taut again. So when it feels taut again, it will what? After this point, will again start to go to the other side, but now the string becomes taut. So when the string becomes taut, you will have the remaining part of the simple harmonic motion on the other side. You have the other part of the amplitude over here. Can you see what's going on? It will go 1 meter. It will go 1 meter. Amplitude is 1 meter, right? It will go the amplitude of 1 meter. So amplitude will be 1 meter. Okay, so basically what's happening here is your simple harmonic motion is split, SHM. Your simple harmonic motion is split at the two ends where the string is taut. So you will have two centers for your simple harmonic motion. There will be two centers. In between the string is slack, and then in the portion where the string is slack, the particle will move with constant velocity. And then after it comes to this point, the natural length on the other side, the string again starts to feel taut, and then it will move over here because it has a maximum velocity, right? At this point, over here, the object, the particle has the Vmax. So it will move over here, and then when it starts to go over here, the string starts to stretch. You agree the string starts to stretch until it comes to velocity 0 at the amplitude. And then again the particle will start to move back. Are you with me? Again the particle will start to move back, and it will increase in velocity until it reaches the center. Okay, are you paying attention to this? And then what's happening at the center? The string becomes slack again, and it moves through this section again with constant velocity, the Vmax, constant Vmax velocity. And then you again reach the center of the SHM again on the other side. Then from this point onwards, again you you perform the remaining part of the simple harmonic motion, and you come back to where you started. Can you guys see what's going on here? So your task is to find the total time taken for one complete trip, because they're asking you to find the time taken until P returns to its starting point for the first time. So I think you can see for P to return to the starting point for the first time, there's a large trip that it needs to cover, right? Are you with me? So first things first, the thing is the time taken to move on the SHM. Even though the SHM is split over the two ends, okay? So what's the time normally you can see we still perform a complete SHM, right? Even though it's split, because you can see you come from here to here. Look, you come from here to here while you're moving from the amplitude to the center. You know the time taken is a quarter of the periodic time. Isn't it always simple harmonic motion? The time taken to come from the amplitude to the center is a quarter of the periodic time. Okay, so over here, the maximum, the constant velocity, you will have to do it by using, or do we need to use any simple harmonic motion equations for constant velocity? No, you can go with M1 equations. S equals ut, because there is no acceleration involved at all. And then on the other side, again, you have what? On the SHM side, you have again a quarter of the periodic time. Are you with me? And then again, you start coming back from the center to amplitude to center. Again, that's a quarter of the periodic time. And again, you make the return join, right? Coming back through the constant velocity again. And then again, you come over here and you have a quarter of the periodic time again. Are you with me? So what's the total time altogether taken for the simple harmonic motion parts only? So on the simple, I think you can see we perform a complete SHM, right? There's a complete SHM on the two ends. So since you're coming back to the starting point, you have the full complete periodic time. Because T over 4 plus T over 4 plus T over 4 plus T over 4 is a complete oscillation, complete T, right? Are you with me? That's complete T. The only times you need to find here is what? You have to find the time taken to come from here to here. This T1 should be found. And again, this time, these two times needs to be found. Coming and going. They are the same. They are the same. This time to take and come from here to here is the same. Are you with me? So let's find the time taken to move on the SHM. Time taken to move on the SHM. So time taken is 2 pi over omega. We start from the amplitude, right? The question says very clearly we start from the amplitude. Okay, so here T over 4, T over 4, T over 4, T over 4. So the SHM occurs at the corners and the time taken for the SHM part is 2 pi over omega. Are you with me? What was omega? I think omega square was 125 over 8. Are you with me? Omega square is 125 over 8. Can you simplify? So omega is root 125 over 8. Can you simplify? So keep the pi out, just simplify 2 over root 125 over 8. How much is it? 2 over root 125 over 8. So I get 4 root 10 over 25 and pi. So I did not type the pi in the cal. I just gave this other part. I just gave this section in the cal. I just typed this whole thing in the cal exactly as is 2 over root 125 over 8 and I got 4 root 10 over 25. Don't forget the pi. Are you with me? That's the time taken to move under SHM. Is this all we need here? No, we also have to find the times the particles moved under constant velocity. How do we find that? So to apply S equals UT, I think first thing is we need to know this constant velocity. First we must know the velocity. How do we find the velocity? We know it moves with the Vmax. Isn't it? We know the particle moves through this the middle section while the string is slack. It moves with the maximum velocity of the SHM. So therefore we apply what? We can apply V square equal omega square A square minus X square. Are you with me? So V square equal omega square is 125 over 8, right? Amplitude is 1. 1 square minus X is 0. Can I have the answer here? So V is root 125 over 8, right? How much is it? V is root 125 over 8, which is how much? This is the Vmax. Vmax occurs when X is 0. X is measured from the center. So even though, so at the center, X is 0. You measure X from the center, right? Even over here, we measure X from the center. So X is 0. So third answer, 5 root 10 over 4. X is the displacement you measure from the center. So when you come to the Vmax, at the Vmax point, X is 0, right? You measure X from the center, not from O. You measure X from the center. Always X is measured away from the center. X is measured in this manner, right? X is measured from the center, not from O. When you reach the natural length, the X becomes 0. Are you with me? That's Vmax. And what about the time taken? So with this velocity, how much of a distance are we traveling to apply S equals UT? How much of a distance are we traveling? 1.6 plus 1.6 for one journey. Can you see? For one journey. So S equals UT. So S is 1.6 plus 1.6, right? For one journey on the way it's coming. So U is 5 root 10 over 4 into T1. So 1.6 plus 1.6 is 3.2 into 4 over 5 root 10 equals T1. Can I know how much is T1? 3.2 into 4 over 5 root 10. How much is it? The exact answer? So we don't get an exact answer here, right? So let's leave it like this. 3.2 into 4 is 12.8. Let's leave it like this for now because this is not the final answer. I think when you give this in the cal, you get a decimal. Okay, and then what's the total time taken for the for P to return back to the original position? So total time taken to return. What's the total time taken to return? The time taken under SHM plus what? Is it just the T1? Because I think you can see T1, you have one journey when you're coming and another journey when you're going, right? So there are how many T1s? There are two T1s. So capital T time taken under SHM plus twice of this T1 time. Are you with me? Because this T1 time we found to move this distance. So periodic time is 4 root 10 over 25 pi plus 2 times T1 is 12.8 over 5 root 10. Are you with me? So let's type the whole thing in the cal. 4 root 10 over 25 times pi plus 2 times 12.8 over 5 root 10. So what do we get? You get 3.2086. It goes on, which means correct to 3SF, 3.21 seconds, correct to 3 significant figures. So type this in the cal and check. Type it correctly and you should get this answer when you type this. So you can see now how springs and strings are so vastly different because of the way it moves. Okay, because when the string is slack, the particle will move with constant velocity. So that's the major difference. So this is what you need to understand, the difference between strings and springs. Okay, so and also there will be two centers in the SHM always because the SHM is split at the two ends. So when the SHM is split at the two ends, you will have two centers for the SHM. Okay, so that needs to be understood here because when you reach over here, when this, because at this point again the string becomes taut, and when the particle moves, this is another center for the SHM because these are the two corners where the string becomes taut. Okay. Okay, so next I'll move to question number 3. They say a particle P of mass 0.4 kilogram is attached to one end of a light elastic string of modulus of elasticity 24 newtons. So lambda is 24 newtons. Natural length is 1.2 meters. The other end of the string is fixed to a point A on the smooth horizontal table on which P rests. Initially, P is at rest with AP 1 meter. So what do you understand? Initially, P is at rest with AP 1 meter means is the string stretched? The string does not compress. So A is 1 point and they are saying, now you know the natural length is 1.2, right? But they say initially P is at rest with AP 1 meter. So if AP is 1 meter, how do you expect this to stay? If AP is 1 meter and you know natural length is 1.2 means the string over here, we don't have compressions. So in this case, the string is completely slack. The string is completely slack. It's on the ground. Are you with me? The string is completely slack. So it's not, we do not do anything with it. The natural length is 1.2 meters. Can you see? So this is 1 meter. Okay, so remember, we can't take an amplitude from here because it's just staying at rest. Okay, so if you stretch in an elastic string, if you stretch it beyond its natural length, whatever the initial amount you stretch becomes the amplitude. But over here, when it's just staying at rest over here, we do not have take an amplitude. Are you with me? Okay, they are saying initially particle is at rest with AP 1 meter. The particle receives an impulse of magnitude 1.8 Newton seconds in the direction AP. So we are giving an impulse. Can you see? Impulse 1.8 Newton seconds in the direction AP. Can you see? So AP direction, that's to the right side. So I gave the impulse 1.8 Newton seconds. Then they are saying, show that while the string is taut, P moves with simple harmonic motion. So how do we do this? Let's draw the diagram again. Okay, so this is the point A. And this is the natural length. So we'll say this is the amplitude. We do not know the amplitude, okay? Amplitude is a constant. Natural length is 1.2. And always you remember the center of SHM is always at the place where the natural length ends. Are you with me? They're asking you to apply F equal ma at a general point, right? So they're asking you to show that the particle moves in SHM. So you have to consider the particle at a general point. Can you see? So over here, definitely moves in SHM only when the string is taut. So how does this work over here? You give the impulse and the particle will start to move and then it passes the natural length and it goes to the other side and the string is taut now. So you have to show it moves in SHM. So how do you do this? The distance is always x is measured away from the center. When the x is measured away from the center, what are the forces acting here? You have the tension, right? You have the tension, right? That's all you have here. So let's apply F equal ma. Away from the center. So what do we get here? Tension is towards the center, right? So minus tension towards the center equals mass. Mass is 0.4, right? Into acceleration is x double dot. Acceleration is x double dot. Are you with me? Okay, so tension is lambda x over L. Tension is lambda x over L. So lambda value is 24 into extension is x over natural length is 1.2. Okay, so how much is the tension? 24 over 1.2 is 20. So tension equals 20x. Okay, tension equals 20x. Okay, so then let's input the value here. Tension is minus t, right? So minus 20x equals 0.4 into x double dot. Can I know how much is x double dot? Minus 20x over 0.4. How much is 20 divided by 0.4? 50. So minus 50x. So can you see the simple harmonic motion, the characteristic equation? Therefore, P moves with simple harmonic motion. Therefore, P moves with simple harmonic motion. That's part A. All right, let's move to part B. Calculate the time that elapses between the moment P receives the impulse and the next time the string becomes slack. Guys, so you can see that the particle receives the impulse when it was already slack, right? Are you with me? And then when you receive the impulse, what happens? With the impulse, what do you calculate? From the impulse, what do you calculate? From the impulse, you can calculate the initial speed that it moves, right? So I equal mv minus mu. Impulse is 1.8. Mass is, how much is the mass? 0.4 v minus 0.4 into initial. Before the impulse, the speed is 0. Particle was at rest. And I know how much this whole thing 0. V equals 1.8 divided by 0.4. How much is it? 1.8 divided by 0.4. 9, right? So that is 9 over 2. Are you with me? I need to realize that this velocity that you achieve it while the string is slack. So when you achieve a velocity of 9 over 2 or 4.5 meters per second, is 4.5 meters per second, right? So when you receive this velocity, the string is in the slack region, right? So which means what's happening over the small part? They're asking you the time taken for the since the moment P receives the impulse until it comes to slack again. Guys, you can see how much of a distance is it moving while the string is slack? How much of a distance is this moving while the string is slack? The particle was 1 meter away from me, right? To go until the how much of a distance why is it moving while the string is slack? You have another 0.2 meters. You have another 0.2 meters to go until the string becomes taut and you have SHM. Okay? Are you with me? So then this short distance that you're moving, so let's say this time taken is T1. So T1 is the time that you're moving under constant velocity. You know when the string is slack, you're moving at constant velocity. The velocity that you get over here will be maintained for this 0.2 meters. Can you see there's a 0.2 meters here? Guys, are you with me? There is a 0.2 meter here to travel, right? So P travels that 0.2 meter with the 9/2 meter per second velocity. Are you with me? And then what are you supposed to do? They are asking you to find the time it takes to become slack again for the first time. So it comes to the point where the string becomes taut and then it will go to the amplitude. The string is still taut and then from the amplitude it will start coming back towards the center, right? And what happens at the center? At the center, what happens? You get the Vmax and and when you are at the center, the string becomes slack. So that's what they want, right? They want the time taken for the string to become slack for the first time. So then from the moment where you start until you have to go to the amplitude and then come back to the center. That's the place where the string becomes slack. Are you with me? So if I try to break this down, okay, if I try to break this down, this is how it goes. You start, the particle P starts from here. So look at my diagram. This is the place where it starts. Okay, this is the t equals 0 place because this is where the object was at the beginning. And then it moves this 0.2 meter under constant velocity. And then from here to the amplitude, what's the time taken? A quarter of the periodic time. And then from the amplitude, again, you have to come back to the center, which is what? Again, a quarter of the periodic time. So then this is the place where, so once you come back here, this is the place where the string becomes slack for the first time. Isn't it? So you have to just add the three times here. So this time taken, let's say this time taken here is T1. The time taken to travel the 0.2 meters. So T1 plus quarter of periodic time plus quarter of periodic time. Are you with me? So how do I find the time taken to move under constant velocity? We can apply S equals UT. So S is 0.2, U is 9/2 or 4.5. Okay, into T1. Okay, so this 4.5 is the velocity that you get from the impulse, immediately after the impulse. Okay, immediately after, so with that velocity, you are going to travel this 0.2 meters until, and then that's the Vmax at the center of SHM. So how much is the time? 0.2 divided by 4.5 is 2/45 seconds. Okay, let's also get the time it moves under SHM. So periodic time is 2 pi over omega. How much is 2 pi over omega? Omega is root 50, right? Omega square is 50. So omega is root 50. Are you with me? Omega square is 50. Omega is root 50. Can I know the simplified answer of 2 over root 50? So you type in the cal 2 over root 50. So I get root 2 over 5. So I just gave only 2 over root 50 in the cal. The pi value, you just have to write it down. 2 over root 50 in the cal gives you root 2 over 5. Can you see? So tension is root 2 pi over 5. So that's the time taken, the periodic time. So what's the time taken for the string to become slack for the first time? The time taken for the string to be slack for first time, it's the time T1 plus part of the periodic time plus another part of the periodic time. Are you with me? So T1 is 2 over 45. T1 is 2 over 45 plus 1/4 of root 2 pi over 5 and again another 1/4 of quarter of periodic time. root 2 pi over 5. You could have even added these two and write t over 2. Even that would have been fine. So what do you get here? 2 over 45 plus root 2 pi over 20 plus root 2 pi over 20. When you add it, it's 2 over 45. Root 2 over 20. Root 2 over 20 is 1 over 20 plus 1 over 20. It's 1 over 10. So when you add them together, it's 1 over 10. So root 2 pi over 10. Because it's 2 root 2 pi over 20 when you add them. 2 over 20 is 1 over 10. This is the exact answer, and you could type the whole thing in the calc. 2 over 45 plus root 2 pi over 10. So I get the answer. So this is you could leave your answer in exact form like this, or the answer would be 0.4887. It goes on like that, right? So 0.4887, goes on. So 33 is 0.489 seconds. Okay, so this is the answer. Okay, so then the next part they say the particle comes to instantaneous rest for the first time at the point B. Calculate the distance AB. How do you calculate the distance AB? So A is the place where we start over here, right? Okay, so the particle comes to instantaneous rest at the point B. Where do you come to instantaneous rest? As you know, when you give this impulse over here, it starts to move with constant velocity for the first 0.2 meters. And then at this point, you have the center of the SHM where you have the maximum velocity. And then you go towards the amplitude, right? So what happens at the amplitude? We know when the particle reaches the amplitude, the velocity becomes 0. The acceleration is maximum. X double dot is maximum. X double dot is maximum, but the acceleration is, X double dot is at maximum. The velocity is 0, which means this is at the amplitude. That's the place where you come to instantaneous rest. Are you with me? So that's the point B. They're asking you to get the AB distance. How do you get the AB distance? AB distance is the natural length plus the amplitude. All you have to do is to find the amplitude. Natural length plus amplitude. So how do you get the amplitude? We can go for what? V square equal omega square a square minus x square. Do we know the maximum velocity now? We know that because the particle got the speed 9 over 2 meters per second while the string is slack, you realize that it comes with the same speed when the at the Vmax also, right? Vmax, it's the same 9 over 2 because when the particle receives the speed when the string is slack, it will continue that same speed until it comes to the center. So at the center, you have that 9 over 2 meters per second speed, which becomes the Vmax. So 9 over 2 square, omega square is for the 50, right? Amplitude is what I'm trying to find. At the center, x is 0. You know, x is measured from the center. So at the center, x value is 0 when you are at the center of SHM. Can I have the answer? 45 over 4. 50 comes down as a division equals amplitude square. So A equals root 45 over 4 times 50. So exact answer? 3 root 10 over 20. So AB distance. AB distance is the natural length plus the amplitude because A is the place where the string is attached to the ground. So 1.2 plus 3 root 10 over 20. So we get the answer. Check on this again. Yeah, I think the error is over here, right? Because 9 over 2 square, 9 square is not 45. 9 square is 81. 81 over 4 × 50, so it's 81 here, right? So what is the root of 81 over 4? 81 over 4 times 50. That's 9 root 2 over 20, right? So amplitude is 9 root 2 over 20. So 1.2 plus 9 root 2 over 20. And we get 1 point. The final answer now, it's 1.836396. It goes on for 1.84 meters. Correct to 3 significant figures. Okay. Okay, so next let's move to question number 6. A particle of mass 0.9 kilogram rests on a smooth horizontal surface attached to one end of a light elastic string of natural length 1.5. Okay, natural length is 1.5, mass is 0.9 kilograms, lambda is 24 newtons. The other end of the string is attached to a point on the surface. The particle is pulled so that the string measures 2 meters. So can you see what's happening? You're pulling it beyond the natural length. Remember, the initial distance you pull beyond the natural length immediately becomes the amplitude. Okay, so how much is the amplitude? Natural length is 1.5. You are pulling it 2 meters. So amplitude should be 0.5 meters. Are you with me? And is released from rest. Say the amplitude of the resulting oscillation. You don't even need to draw the diagram here. You need to be able to see it. Amplitude is 0.5. Part A answer. Amplitude is 0.5 meters. Okay. Okay, then let's go to the next part. Calculate the speed of the particle when the string becomes slack. Okay, so obviously to do this, we will go for the F equal ma equation, get omega and the speed of the particle when the string becomes slack. Now by now you know that when the string becomes slack, it means you are at the center of the SHM. Do you remember? Yes. Okay. So when the string becomes slack, that means you are at the natural length. When you are at the natural length, you are at the center of your SHM. Shall we draw the diagram? In one diagram, shall I draw it? When I draw it in one diagram, it looks like this, right? Have they said the place where you are marking on the ground? So we will mark these lengths. This is the place where the string is attached to the ground. This is the natural length. Natural length 1.5 meters. And this is the amplitude. So amplitude is half meters. Amplitude is half meter, right? And you are releasing it from the center. You are releasing it from the amplitude, right? You are releasing it from here. So they say calculate the speed of the particle when the string becomes slack. First, let's get the equation. Let's get the x double dot equal minus omega square x, the characteristic equation. Are you with me? So to get the characteristic equation, what do? We have to consider the particle at a general point. Are you with me? So consider the particle at a general point. And then you know what we should do here. We measure x from the center of the SHM. So you know where the natural length ends. That's the center of your SHM. Are you with me? So x is measured from this point onwards, from the center. Are you with me? Okay, so let's mark all the forces. So you have the tension towards the center. You have the tension towards the center, agreed? That's the only force, right? Because it's a smooth horizontal ground. So you do not have friction or any other force. It's smooth. So we will apply what? F equal ma away from the center. All right, so what's happening here? The tension is minus T. Mass is 0.9 into acceleration is x double dot. Let's get the tension lambda x over L. Lambda is 24 into x is the distance the string has stretched beyond the natural length. So beyond the natural length, it has stretched A distance of x over natural length L is 1.5. Are you with me? How much is the tension? 24 over 1.5 is 24 divided by 1.5 is 16. Yeah. So minus 16x equals 0.9 x double dot. Can I know the x double dot value? Minus 16x divided by 0.9. How much is it? Minus 160 over 9x. Are you with me? So this is the characteristic equation. So you can see we have the characteristic equation for simple harmonic motion. So you can clearly see therefore particle P moves in SHM. And then from here we can get what? Now we are supposed to find the speed when the string becomes slack. Basically over here, right? The string becomes slack means at the place where the string becomes slack, you have the maximum velocity. So all you got to do here is what? We can apply v square equal omega square a square minus x square to find the speed when the string becomes slack. Are you with me? So v is v max, omega square is, so we just found x double dot is minus omega square x. Omega square is 160 over 9 into a square. Amplitude is 0.5 square minus x is 0 because when you add the maximum speed, when you add the natural length, x is 0. X is measured from the center. Okay, so how much is the v value? 160 into 0.5 square over 9 whole thing square root, right? So v equals 2 root 10 over 3 meters per second, which is 2.108. So I'll leave it in exact form. No, it's 2.11, correct to 3s. Okay, is that okay? That's the answer for part B. Okay, so the next part. Before the string becomes taut again, before the string becomes taut again, the particle hits a vertical surface which is at right angles to the particle's direction of motion. Okay, what's happening here? Now, where does the string become taut again? Now, at this point, we found the speed when the string becomes slack, right? Guys, are you with me? And this is the place where the string becomes slack. Okay, so where will the string become taut again? Now you know the particle is on its way here, right? So you know what's happening over here from the amplitude to the center. You have SHM, and after the center, after passing center, you go with what? You go with constant velocity, right? Do you recall? Because the string becomes slack, and this part of the motion goes under constant velocity. So you will keep going under constant velocity until the string becomes taut again, which means when you reach the natural length on the other side. So they are saying before the string becomes taut again, because the string is supposed to become taut again over here. Are you with me? So if you go another natural length 1.6 meter to the other side, at this point, the string will become taut again because this is where it became slack now. And from here to here, it will go at constant velocity and becomes taut again, and then it will perform the rest of the SHM. Isn't it? That's what we learned, right, at the beginning. All right. So they are saying that before it actually comes to this point, they are saying what? It hits a vertical surface. So there is a vertical wall. There is some kind of a wall that's built over here. So it never gets to go to that point. So the particle comes, hits this wall, and it rebounds. So do you see there's a collision? The coefficient of restitution between the particle and the vertical surface is 3 over 5. Okay, so the particle comes and it will hit this wall, right? It will hit the wall at what speed? It will hit the wall at the Vmax speed, right? Oh yeah, the natural length is 1.5. So what is the speed that it hits the wall? The speed that we found here is 2 root 10 over 3, right? So let's say that is V1. And after you hit the wall, what's going to happen? You're going to rebound and it's going to move with what? A different velocity, isn't it? So let's say V and W. So W is the speed of rebounding. I'll use it like this. Are you with me? So V is the speed of hitting the wall and W is the speed of rebounding. So the first thing you should do here is to actually calculate the speed that it rebounds from the wall. So for this, you need to what? Remember M2. So in M2, what was the equation you used? When you hit a wall or when you hit the ground or any a surface that doesn't move, we use the equation E equals to V over U because one object doesn't move. Okay, normally Newton's coefficient of restitution is equal to speed of separation over speed of approach. But over here, since we are using one object is moving, the other one is a wall, or if the other particle, if the other object is the ground, then we are supposed to use E equal V over U. Do you recall? V is the speed of rebound and U is the speed of hitting the wall, initial speed. The speed just before hitting the wall, V is the speed just after hitting the wall. So E is 3 over 5. What is V? The speed after rebounding from the wall. V is the speed after rebounding. Remember, V is final, U is initial. So over here, what's the final speed? Is it V or W according to what I marked? Is it V or W according to what I marked? V is the speed that is after. So what's the after speed here? The after speed is V or W according to what I marked here. The after speed is the after one is W because that's the speed that you rebound from the wall. So that is W over initial speed is initial is this V, right? The V value. The initial speed is this V value 2 root 10 over 3 because you hit the wall with 2 root 10 over 3. That's the initial. So this V is what becomes the U. Are you with me? Then we can get the value of W 3 over 5 V equals W. Let's input 3 over 5 into V is 2 root 10 over 3 equals W. So what do we get here? W equals 2 root 10 over 5 meters per second. Can you see? So it will be, you can see that I think it should be a it should definitely be a lower velocity than previous. Are you with me? So this is the new speed. This is the new speed after the particle rebounds from the wall. Are you with me? Okay, so the question says to calculate the period. The question says to calculate the period. So how do you calculate the period? The period of the, now you need to realize, so when the particle is now moving with this new velocity, you need to realize that this W is the new maximum velocity, right? Are you with me? W becomes the new maximum velocity. Therefore, now when the particle moves, it moves with W speed. It moves with W speed, and when it comes to the natural length, now what's the V max? The maximum velocity is now W. Are you with me? So it is definitely a value lower than the previous value because you hit the wall, you lost some energy, right? So the W value that you get over here, the new V max is definitely lower than the previous V max. You can get the decimal values and check. Are you with me? Okay, so this is the new V max. So with the new V max, how do you think it affects the period? So period is 2 pi over omega, right? So is the will the omega be affected that we previously calculated? You can see in the previous part we calculated omega as root 160 over 9. Can you see? This is the omega square value. Are you guys with me? Will the omega change? No, right? I think you can see omega is depending on F equal ma. And you can see the tension, mass, these guys don't change, right? So the tension, lambda x over L, the extension. So this equation, if you go to use it again, the lambda, since the natural length, they are all the same, the omega value doesn't change. Okay. So tension is lambda x over L, lambda is 24, extension is at the general point x, natural length is 1.5. So this equation is completely preserved even for the new simple harmonic because you need to realize now we have a new simple harmonic motion. So the period will not be affected. So period will be T equals 2 pi over omega. Omega will not change because you can understand that if you try to use this equation again under the new value of W, that won't make an impact. So omega is root 160 over 9. Can I have the simplified answer? Can I have the simplified answer? So 2 over root 160 over 9. Decimal, first we'll get the third answer. You can give it without the pi in the cal. If you give it with the pi, you'll get a decimal. So type this in the cal without giving the pi. 2 divided by root 160 over 9. Then that gives you the third answer, 3 root 10 over 20, and you give the pi on your own. Because if you type the pi in the cal, it will give you a decimal. So that's the periodic time. Can you see that's the period? Okay. So which is 1.49018824 seconds or 1.49 seconds correct to 3 significant figures. Are you with me? Okay. And then the next part they wanted to find is the amplitude. Roman number 1. Okay. So what about the amplitude? Okay, and then they are asking to calculate the period that's done and the amplitude of the oscillation which takes place when the string becomes taut once more. Okay, so over here the period means the time taken to move under SHM. So you don't need to worry about the volley. All they are saying is after with the new speed, with the new Vmax that you are getting. So what would be the periodic time for the new motion? So that's why I found this whole time the time taken for a complete oscillation under SHM. So that's what they want. So they are asking you to calculate the new period. So over here the period it's not affected because omega doesn't change. If you apply F equal ma even for the new system, this equation will come exactly as it is. There won't be any change. So omega doesn't change. However, amplitude will be impacted, right? Why? Because now you have at the center, now you have a lower speed. Do you think you'll be able to achieve an amplitude of 0.5? No, it should definitely be what? Amplitude lower than 0.5 because now you have a lower Vmax because you hit the wall and you're coming back. Now the velocity, the Vmax is lower than the previous Vmax. So if you're having a Vmax lower, the energy is lower, which means this string will not be able to pull off an amplitude of 0.5 now. Should surely be lower than 0.5. Okay, how do we find the new amplitude? We can again use V square equal omega square a square minus x square. So V is the new speed. That is the W we found over here. Can you see? The W is 2 root 10 over 5 whole thing square. Omega square is 160 over 9, right? Into a square, x is 0. Amplitude is what I'm trying to find. Under the new speed, what's the new amplitude? So 2 root 10 over 5 square is how much? When you in the cal? 2 root 10 over 5 whole thing square gives me 8 over 5. Are you with me? 8 over 5 into 9 over 160 equal a square. And get the a value. So 8 into 9, 5 into 160. So it's 9 over 100. A square is 9 over 100. A is x, root 9 over 100, which is 3 over 10. Or in other words, how much? 0.3 meters. So amplitude. Can you see it's lower than the previous amplitude? Previous amplitude was 0.5, but now the new amplitude is 0.3 meters. So this is the amplitude under the new motion. Okay. Okay, so we'll move to the next question. Question number 8. A particle P of mass 0.5 kilogram is attached to one end of a light elastic string of natural length 0.4 meter and modulus of velocity 30 newtons. Natural length is 0.4 meter and lambda is 30 newtons. The other end of the string is attached to a point on the smooth horizontal surface on which P rests. The particle is pulled until the string measures 0.6 meters and released from rest. So you can see here, natural length is 0.4 and they are pulling the string until it measures 0.6 meters, which means how much is the amplitude? Immediately, the amount that you are pulling beyond the natural length becomes the amplitude. So the amplitude is 0.2 meters. And you are releasing from rest. So they are asking calculate the speed of P when the string becomes slack for the first time. So obviously, before you go to do that, we will draw the diagram. So this is the point where you are here, where it's fixed to the ground. Okay, so point O is the place where the particle, where the string is fixed to the ground. Okay, and then natural length is over here, right? Natural length is 0.4. And then amplitude was 0.2 because they say they are releasing it when the total length of the string is, they are releasing it when the total length of the string is 0.6, which means amplitude is 0.2 meters. Okay, so then to prove the particle, so first thing you should do is obviously go and show that it moves in SHM, because to get the speed we need the omega, right? We are asking the speed when the, at which the string becomes slack for the first time. So we'll use this at a general point. So consider the particle, it's not at the amplitude, it's at a general point. Can you see? Consider the particle at a general point. And then the distance that we take this distance as x, right? Measured from the center, this is x. And this is the center of the SHM. This is the center of the SHM. So let's apply F equal ma towards center. Let's apply F equal ma towards center. F equal ma away from the center, right? So you have tension towards the center. So you have tension towards the center. So that's minus T equals mass is 0.5 into acceleration is x double dot. So tension is lambda x over L. So lambda is 30. Lambda is 30. Extension x is x over natural length is 0.4. How much is 30 over 0.4? 30 over 0.4 is 75. So t equals to 75x. So minus 75x, t is minus t is 75x. 0.5x double dot. So minus 75x over 0.5 equals to x double dot. 75 divided by 0.5. This is minus 150x equals to x double dot. Can you see? So this is the x double dot equation. Therefore, P moves in SHM. Okay, so P moves with SHM. And then you have to find the speed with which the string becomes slack for the first time, which means what? You have to find the Vmax, because you know the moment you reach the natural length, that's where you get the Vmax, and that's where the string becomes slack for the first time. So all you have to do is apply V square equal omega square a square minus x square. So at the maximum speed, Vmax, omega square is 150. So the amplitude is 0.2 square minus x is 0. Okay, so how much is it? 150 into 0.2 square gives me 6. So V equals root 6 meters per second. This is the Vmax. So this is the speed when the string becomes slack for the first time. This is the speed. Okay. And then we'll move to part B. The string breaks at the instant when it returns to its natural length for the first time. So when you come over here to the natural length, they say the string will break. The string will break means you, so if I draw the diagram here, Basically, the particle reaches the natural length. This was the amplitude, right? So the moment the particle reaches the natural length over here, the string is gonna break, which means do we have any attachments with the string anymore? No. Which means there won't be tension anymore. There won't be any attachment with the string. The string is completely gone. So you don't need to even draw the string. So now this particle is going to move what? With this Vmax that you found, right? So they are saying the string breaks at the instant when it returns to its natural length over here for the first time. When P has traveled a distance 0.3, okay, so the particle will travel a distance of 0.3 meters. Can you see? So the particle will move a distance of 0.3 meters. So when P has traveled a distance of 0.3 meters from the point at which the string breaks, so this is the place where the string broke, the surface becomes rough. Can you see what's going on here? So after the point where the string breaks, 0.3 meters after this point, from this point onwards, the flow now becomes rough. Can you see now? Remember, the particle is moving on without the action of the string. There's no string, there's no tension because string has broken. So they are saying the coefficient of friction between P and the surface is 0.25. So over here, the new value is 0.25. The particle comes to rest capital T seconds after it was released. So obviously, when there's friction, now there is an external force. When there's a friction, there's now an external force. So the particle will come to a point and it will come to rest. It will start to lose its speed. Until this point, it came with Vmax, right? Until over here, it came with the Vmax, √6. Okay, it came with √6 meters per second, right? From the natural length, and then the string is broken. It came 0.3 meter. It came 0.3 meter on the smooth flow, and then after 0.3 meters, the flow becomes rough. So then it will keep moving until it loses the velocity and becomes 0. So it comes to rest. They're saying the particle comes to rest capital T seconds after it was released. So capital T seconds means you are releasing from the amplitude, right? So you recall you release the particle from the amplitude. So they are saying the particle comes to rest capital T seconds after it was released. So for all of this motion, it's capital T seconds. They're asking you to find the value of capital T. So how do you do this? How do you break the time? The first time you need to take is the time taken to come from where? The amplitude to the center. What's the time taken to come from the amplitude to the center? What is the time taken to come from the amplitude to the center? What is the time that we say? I mean, not the value, but what is the general notation? It's a quarter of the periodic time, right? Amplitude to center. So it's a quarter of the periodic time. So that's the first time. And then you have to find the time it moves under constant velocity, because you need to realize this 0.3 meter, it's moving at constant velocity. The string is broken. And then after that, there's another time it moves under deceleration. That's the T2 time. So you have to get this 3 times and add them together. Are you with me? I think the most challenging part here is this. We need to get this, we have to get this, the deceleration here, right? Are you with me? Because we need to get the, we have to get the time taken. So how do we get, shall we consider this part first and get this time? Because this is the time that is the most time consuming to get. Okay, so how do we do this? So consider the particle while it's moving. So what are the forces it has when it's on this particular, when it's moving over here, it will have, the particle is moving to this direction, right? So it will experience friction. Are you with me? It experiences friction, and that will be the maximum friction. Then particle will have normal reaction. It has the weight. It has the weight. So what do we apply here? Are you with me? Shall I draw it separately over here? What am I trying to do now? What am I trying to find here? I'm trying to find what? The deceleration. Because you need to realize from here to here, when the flow is rough, there is a deceleration. You have to apply F equal ma from here to here and find that deceleration. Are you with me? So you have what? Because the particle is moving on the rough flow, you will have friction. So that will be the F max friction because it's moving. Are you with me? So it will be the F max friction because it's moving. And also you'll have normal reaction, right? Upwards and down you have the weight. And down you have the weight, mg. So let's apply F max equal mu r. So F max equal mu is 0.25. What's the normal reaction? Normal reaction is equal to the weight, mg. I think mass was 0.5, right? So G is 0.5 G. Are you with me? Can I know this value? 0.25 into 0.5 is 0.25 into 0.5 is 1 over 8. 1 over 8 G. Are you with me? And then let's apply F equal ma in the direction that the object is moving. So I'm considering the part where the particle is moving under friction. Okay. For motion under friction. So the force, the force that you are experiencing here, you don't have any frontward force, right? The only force you have is the friction, which is backward. So minus friction, mass is 0.5 kilogram into acceleration is what we are finding. So friction is 1 over 8 g. 0.5 into a, what do we get for acceleration? 1 over minus 1 over 4g, right? Then the half goes to the other side. Okay, so we have the acceleration. Now can't I find the time it takes to move this particular part under friction? We can use what? V equals U plus AT. The time taken to move under friction. So final speed is 0, right? You get the final speed 0. Initial speed is the root 6. Acceleration is minus 1 over 4g into time taken is I have marked as T2. So plus 1 over 4g into T2 equals root 6. T2 equals 4 root 6 over g. Guys, are you with me? 4 root 6 over g is T2. So I have, this is the most difficult time to find here because there's a deceleration involved. So I had to apply F equal ma for the deceleration part, get the deceleration, and then apply V equal U plus AT. Then the next part is the time for motion under constant velocity. So for motion under constant velocity, we can apply S equals ut. We can apply S equals ut. So S is 0.3, U is, you are going to move with the root 6 speed, right? And time is T1. So 0.3 over root 6 is the time T1. And then the final time is the time taken to move under SHM. So next one for motion under SHM. So for motion under SHM, the time taken will be, it will be T over 4. So T is 2 pi 1/4 of 1/4 of T. T is 2 pi over omega, right? So 1/4 of 2 pi over what's omega? The omega value is root 150, right? So that gives pi over 2 root 150. I cut the 2 and 4. 2 times 1, 2 times 2, pi over 2 root 150. Okay, so total time taken. So total time taken equals, all these times you have to add, right? Pi over 2 root 150 plus 0.3 over root 6 plus 4 root 6 over G. So you can give, when you use G as 9.8, you have to use, give the answer 3SF or 2SF. So I will write here G 9.8. Okay, so let's give the answer to either 3SF or 2SF. Type everything in the calendar and get the answer. So this gives us 1.25052120. It goes on. So 3SF answer 1.25 seconds. Correct the 3SF. That's the answer. This is clear. Okay.